All right, so I'm going to show you a cool thing in preparation for recalling some spring stuff. So the cool thing I need to show you is a Calc 2 exercise. So recall Calc 2. You guys remember Calc 2?
Not as much as I should.
All of Calc 2? Okay.
Not at all.
What's a McLaurin series?
They're like the zero.
Taylor series is zero.
Yeah, it's a Taylor series centered at 0.
In only 2 dimensions, right?
No, in only 1 dimension, friends. This is a Taylor series in 1 dimension. So, what I need you to remember about, should I just make one of these for kicks?
Yeah.
Sure.
Okay, so let's make the Taylor series for e to the x. You guys remember the idea of a Taylor series?
Yeah.
Yeah.
What do?
You take the first point and you evaluate it at the original function.
Gross. Why would you do that?
Or you just look that up.
No. Don't look up a formula. Think with your brain. What do you do?
Find the
Put
dumbest
the value of
approximation.
that at 0.
Add it to the next dumbest approximation.
Yeah, really you're just doing approximations in order of dumbness, right?
Yeah.
Or you're just assuming it looks like a polynomial, right? So like, if I assumed this looked like a polynomial, it would probably look like some first number plus some second number times x plus some third number times x squared plus some fourth number times x cubed plus, oops, that was supposed to be a plus some fifth number times x to the fourth. And then I realized that I was dumb in my numbering scheme here. And I should have counted like a computer scientist instead of like a child with sheep. Why should I count this way?
Because the first one's x.
It makes it easy to remember what to divide by.
Yeah, so that they agree, right? Okay, so if you assume this, and then you think to yourself, okay, if I plug in 0, e to the 0 should be the number 0 plus,
0, 0.
yeah, all the rest of that crap should be 0, right? So the first number should just be e to the 0, which is 1. So over here I'm putting my e to the x is 1. First dumbest guess. You guys with me on that?
It's a really dumb guess.
That's a super dumb guess. You have some exponential function, right? And you're saying it's approximately this constant 1.
Yeah. Yep.
Is that true? No. Is it true near 0? Yeah, sure. If you're pretty close to 0, right, e to the thing is pretty close to 1. So if you want a better approximation, what else do you do? Yeah, go to the next thing. So how do I get rid of this x? What's a thing you guys know learned in calculus class that gets rid of x's? Yeah, hit this thing with a derivative. So this was a eval at 0, right? This is going to be, take the derivative of both sides. What do you get when you differentiate e to the x? E to the x, that's convenient. And on the other side you get the first number, right? Because the 0th number is, its derivative is 0. So you get the first number times, well, drop the power, x to the 1 lower power, that's all 1, plus twice the second number times x now,
Wait. Oh,
plus
3 x squared.
3 times the third number x squared,
And so on.
and so on. Right, so out here someplace there's going to be an n x to the n minus 1, right? Oops, n times number n x to the n minus 1, right? And then we'll keep going after that. You guys all good with this? Then what do you do with that?
Gotta keep going. In value, yes, maybe?
Yeah, evaluate. Where are you guessing? 0, so you evaluate at 0 again. And you get that e to the 0 is
Number one,
the first number, right?
which is one.
Okay, so the first number is also 1. So I got 1 plus x is my second dumbest guess. So that's a line that looks like this. So basically I matched the tangent line, right? In fact, that is the tangent line at 0. Right? Okay, so then you make your next dumbest guess, which you do by
Taking two derivatives.
differentiate again. And this is where something interesting happens, so I'm actually going to do this one. So we differentiate again, and we get e to the x is
Number
2 plus
6 number 3 x.
3 times 2 number 3 x plus
Something something.
4 times 3 number 4 x squared plus and so on. Right? And then out here someplace, way down the line, there's a n minus 1 x number n x to the n minus 2. And continue. Guys all good with that? Okay, and what do I do with that thing?
solve for
No.
number two. Plug in the back in the e to the x.
No.
X is. Plug in 0.
Yeah, plug in 0. So evaluate at 0, you get e to the 0 is twice the second number. Now you have to solve, right? So what's the second number? 1/2. So I get plus x squared over 2. Guys with me? Okay. You would take another derivative, evaluate it at 0. What are you going to get? You're going to get e to the 0 is 3 times 2 times number 3.
Looks like a factorial.
Yeah, and it's got to be a factorial, right? You guys see that? So if we kind of continue this process where we differentiate and then evaluate at 0, and then differentiate and then evaluate at 0, and then differentiate and then evaluate at 0, what we're going to get is a series that looks like this.
So this is kind of like the cleanest Taylor polynomial in a way, right? Because we just have
Yeah, for sure. In general, right, this guy would be f evaluated at 0, and then this guy would be f prime evaluated at 0 times x, and then this would be f double prime evaluated at 0 divided by 2 times x squared, and then this would be f triple prime evaluated at 0 divided by 3 factorial times x cubed, and so on. But this one's chill, right? So all the derivatives are the same as the function you started with. So this is the easiest Taylor polynomial to make. So, okay. All right. So to observe the cool thing, I need this. Okay, so what is your first dumbest guess for sine and cosine?
sine 0, cosine 1.
Yep. Sine's nothing, cosine's 1. Okay. What's the derivative of sine at 0? So cosine evaluated at 0, which is 1. Okay, what's the derivative of cosine at 0?
Negative sine.
Negative sine. When you evaluate, you get 0. You guys with me? Maybe if I wrote these down in here, it'd be more fun. So I have 0. This one's 0 x's. This is 1x. Okay, how about this guy?
0.
How about this guy?
Negative x squared over 2.
Zero, 1, 2. No.
Negative.
Okay, so this guy was negative sine, right? Evaluated at 0. This guy was,
Negative cosine.
that guy was negative cosine evaluated at 0.
Positive.
Positive.
Cosine's derivative is,
Negative, yeah.
thank you. No, cosine's 1.
You need to shift something.
Oh, yeah.
Sorry guys, that's my bad. How do these derivatives work again? So cosine, right? Cosine of 0 is 1, so I'm not talking about sine, I'm talking about cosine itself. And then this is minus sine evaluated at 0. And then this one should be negative cosine evaluated at 0. So this should be
Negative x
minus
squared
1 over 2 x squared.
We're always dividing by n factorial, right?
Yep,
That's
and
what
we're
we
always
follow.
dividing by n factorial because of the way we made the formula. So this guy should have been sine evaluated at 0. This guy was cosine evaluated at 0. This guy was
Negative sine.
negative sine evaluated at 0.
So the next one should be negative cosine
So the next one should be negative cosine
evaluated.
evaluated at 0, which means I'm looking at negative 1 over 3 factorial x cubed. And down here,
It's positive sine.
I should be looking at positive sine evaluated at 0, which is
0x.
0. So I got 0x cubed. You guys, what's going to happen here?
They alternate.
They alternate between 0 and something, right? And then the ones that are there alternate between positive and negative. You guys see that? So I'm going to get plus 0 plus 1 over, what's the next one that's going to be here?
5
5
factorial.
factorial.
5 factorial x to the 5th plus 0
Was 1 over 7 factorial times x to the 7.
minus 1 over 7 factorial x to the 7th, and kind of so forth, right? And on this guy, I got a plus 1 over 4 factorial x to the 4th
Minus.
plus 0 minus 1 over 6 factorial x to the 6th, and kind of so on.
Isn't that why sine is odd and cosine is even?
Yeah, right? Because odd and even are things about the powers of polynomials, and sine is only made of odd powers. Thus it's odd. Cosine's made out of even powers. Thus it's even. Yeah, that's right. Maybe you wouldn't say that's why, but that's maybe that should have been clear when I started because there's odd and even. So, what do you notice about these guys? And that?
It almost feels like you could somehow mash those two together to get that
You guys see that?
x,
Like,
but it turns out you're going to need an I to do that.
if I kind of cram these together, I get 1. If I cram these together, I get x. If I cram these together,
You get
I get-
negative.
oh,
So
frick!
that-
Just subtract them.
Right? So like, these two work, That one's off by a minus sign. These two,
That one's also off by a minus.
also off by a minus sign.
Those
These
will work.
ones work. These ones work. The next one's going to be off by
Minus sign.
a minus sign, and the one after that's going to be off by a minus sign. So then you got to wonder, is there something I know that goes around in da-da, na-na, da-da, na-na, right? Like, is there a thing I know that does that? Like, do I know a thing that goes positive, positive, negative, negative, positive, positive, negative, negative?
Square root of negative 1.
And the square root of negative 1 is just such a beast. So you might think to yourself, like, okay, if I plug in e to the I theta, or e to the I x, right, like the way I would do this is I would take the Taylor polynomial, or the Maclaurin series that I just made, and shove ix into it. So I'm going to get 1 plus ix plus, oh yeah, it'll really be minus, right? Because it's ix quantity squared. So it'd be negative x squared over 2. And then there's a plus, oh no, it's still minus, right? Because there's at least 2 there. And then there's 1 extra. So I got a minus ix cubed over 3 factorial. And then what's your next one going to be?
Plus.
It's going to be plus x to the 4th over 4 factorial, because I to the 4th is negative 1 times negative 1, which is positive 1. Cool. Okay, so then I might notice, okay, so the even ones look like,
Cosine.
the even ones are cosine. Right, like just straight up. That stuff is cosine. So you get cosine x. Like that's those pieces. Then what's up with the other ones?
I sine.
Yeah, it's I times sine x. You have to factor an I out of the whole thing. Oops. Let me do squiggles. Squiggles.
Is this how Euler got this?
Yeah.
Cool.
Yeah, these are a rad thing actually, because Euler gets a shitload of credit for what's essentially noticing something about Taylor polynomials, right? Like you calculate the 3 obvious Taylor polynomials and just go, oh, those look kind of similar. Super badass. Well, I mean, first you have to develop a concept of like I as a number, and then like demonstrate some things about being able to take I and multiply it around a little bit. This is not a trivial result. With modern notation, it's totally trivial. Right? But back in the day, before modern notation, this was a major bear to notice that.
Didn't they just write a bunch of paragraphs and stuff?
Yeah.
instead of-
So the thing I want you to take from this is Euler's. That one's Euler's. This one's Euler's formula, I think. There's also Euler's identity. I always forget which one's which. The other one is e to the I pi. What's e to the I pi? Negative 1.
So which one's the official proper way to write it? The e to the I pi plus 1 equals 0, or e to the I pi equals negative 1? 'Cause I know that some people really stick.
Well, there's 2 more.
Oh, I don't know. I've read it this one. I don't know. I'm not a complex analyst. I'm a complex dynamicist. So.
I'm guessing that that second equation came from plugging pi in for x.
Yep, exactly. If you plug pi in for x, right?
Sine becomes 0.
Cosine of pi is negative 1, and sine of pi is 0.
What's the difference between those two things you just mentioned? What you are and what other people are?
Some people are complex analysts, which means they spend time thinking about doing calculus in the complex numbers. And what I is a complex dynamicist, which means that I think about function iteration in complex numbers. So they think about like doing calculus as a whole and analyzing like the Riemann zeta function is a really good example of a complex analysis idea. I think about things more along the lines of, what if I just took the complex numbers and whacked them with a hammer over and over again in the exact same way?
Nice.
Like, is there any kind of theory that might come out of that? There is. There's some cool stuff. Like Mandelbrot set is kind of the beginnings of complex dynamics. Okay, so what I want you to take from this is Euler's, because we'll need it for springs.